So now we'll try to understand how we can determine the uh, works and different type of heat. Like if I see for the case of turbine work, how we can find the turbine work. So turbine work, we can find that mass of steam, rate of flow of mass of steam into S3 minus H4 enthalpy at 3 minus enthalpy at 4 because at 3 the enthalpy is no minus H4. Okay, if I talk about the comfort, that will be m dot H2 minus H1. The heat supplied will be m dot, that is mass of steam actually, that is H3 minus H2 because H3 volt, and QC is equal to m dot H4 minus H1. So the network, if we want to get network is equal to, that is turbine work minus pump work is equal to, if we want to find out per kg mass of steam, then this will be S3 minus H4 minus H2 minus H1. We can also say it S3 minus H2 minus H4 minus H1, which is equal to S3 minus H2. What is S3 minus H2? S3 minus H2 is actually the previous per unit mass I have taken minus H4 minus H1 is what? H4 minus H1 is actually condenser, yeah, QQ reactive. So this is actually the work net, or we can say that turbine work minus pump work. Fine. Now will try to understand. Let's say that we want to find out S3 here. S3 will be, let's say, somewhat 2948 kilojoule per kg. Okay, and H4 here is something. H4 here is, let's say, 1996 kilojoule per kg. So how we are getting these values? How we are getting? We'll try to understand that how these values are decided or evaluated. Okay, so let's again draw. No, I'll not first draw. First, I'll draw the boundaries. Boundaries. What boundaries? I'll draw the boundary of vapor region, liquid region, saturated liquid region, and the saturated vapor region. I'll draw. Okay. So whenever uh, I show that, whenever I show that the enthalpy here is H3 and here is this, and enthalpy here is decreasing. Let's say here enthalpy will be H2 is equal to, let's say, 313 kilojoule per kg, and here is 2948 kilojoule per kg. So here actually enthalpy is continuously decreasing. So it will decrease till what? Till what extent? And it will decrease till what extent? And this will decrease till what extent? So these lines will meet somewhere. What is this? Where enthalpy may be somewhere zero. So what is that line? So that line is actually, scientists have decided that line is the triple point, triple point of water. That's why we usually draw the TS diagram for the vapor phase or the water liquid vapor phase. So we can also show that this is our TS diagram where the enthalpy is zero at the origin. But we usually draw this TS diagram from here for our convenience. Okay, because otherwise it will be very far away from the origin. That's why we usually take TS axis here only. So now we can understand some of the things, that what is H3. if you want to find out H3, there are some things to understanding. So we'll show that H3 is actually the area of what? 0, 2, 3, 4, B, 0. What are these points? I'll show. I'll show all these points. This will be point. Actually, I have taken here. This is the condenser pressure. Okay, and this will be like this. Fine. And I'll show some points. Let's denote all the points. I'm showing the points here. 1, 2, this is 3, and 4. Okay, I'll show some more points. Let's say this is A and this is B. So 0, 2 or point 0 is this. 0, 2, 3, 4, B, 0. This whole portion is showing actually H3. Okay, and what about area H4? If we want to find area H4, this is actually 0, 2, 3, 4. H4. 0. Actually, this H4 will find. Let's denote from this color only. Also, sorry, 0, 1, 4, B, 0. This is S4. So what is actually the turbine work? H4 I will show as something like this. This is the S4. So what is the turbine work? That is H3 minus H4. Okay. So just subtract the H3 minus H4, then you will get this portion. I'll color it. Mm, this portion. This is the H3 minus H4. What is this? 0, 2, 3, 4, 1, 0. This is H3 minus H4. That is the turbine work. Fine. So now I will divide. I will explain some terms here. The first one is the specific steam consumption or steam rate. Specific steam consumption or steam rate. Or in short, we can say that specific steam consumption SSC is equal to it is actually the mass flow rate of a steam required for 1 kilowatt power output. So mass flow rate of steam per kilowatt power output is called specific steam consumption. So actually we know that what is power? Power is equal to mass of steam rate into network output. So from this equation, if we'll put here, so we'll get that specific steam consumption is equal to 1 upon small w net. This is actually the kilojoule per kg. So specific steam consumption will get that uh, kilogram per kilojoule or kilogram per kilowatt second. You can also write fine. In other words, if you want to write in terms of the kilowatt hour, so we know that 1 kilowatt hour is equal to 3600 kilojoule. So specific steam consumption, we can write that this will be, or you can write that 1 kilojoule is equal to 1 upon 3600 kilowatt hour. So we want to write this kilowatt second in kilowatt hour. So actually we have to divide W naught by 3600. So we'll get 3600 divided by W net. So you will get in this kilojoule per kilowatt hour. This is the specific steam consumption. Let's talk about the heat rate. What is heat rate, HR? Heat rate. It is the amount of heat input required for 1 kilowatt of power output. It is the heat required. The name as it suggests that heat supplied in kilowatt divided by power in kilowatt. Okay, so we can write heat rate is equal to mass of the steam into heat supplied into, or actually I have to write this small. Okay, divided by power dot s into W net. So this is the heat rate is actually Q supplied upon network, or we can say this is the inverse of efficiency. Heat rate is the inverse of efficiency. Fine.